The third solid design principle that I want to look at is the open-closed principle. The open-closed principle comes from Bertrand Meyer's book, Object-Oriented Software Construction, and tells us that software entities should be open for extension, but closed for modification. The open-closed principle is closely aligned with interface segregation and Liskov substitution. We need to segregate interfaces based on the needs of the client classes. This often creates a class that's generally closed and doesn't need further modification. Liskov substitution assures that the subclasses are proper extensions of the superclass, which means the superclass is open to extension. The open-closed principle summarizes the goals of the interface segregation principle and the Liskov substitution principle. A design with good interface segregation and Liskov substitution applied tends to have classes which can be extended by creating subclasses. There's no need to modify classes to add new features. The reader class seems to fit this pattern. Consider this example of the reader class. I want to focus on the read method, defined here as just an abstraction. Here's an implementation of the read method for CSV files. This will create instances of sample objects by depending on the CSV module to properly parse the physical format, and this method applies the float function to convert strings found in CSV files into float objects that the application uses. What if we have to do more complex parsing? For example, what if each column had the unhelpful letters RPM and looked like this? A simple float function is no longer appropriate. We need something a lot more sophisticated, but the open-closed principle warns me away from modifying my existing code, so I'll need a better design that lets me add this feature by extension. This is why a builder can be very handy. Using a distinct builder allows me to revise readers using one of a variety of external builder objects to build sample instances. In this case, I've summarized the builder as an object that has this kind of type hint. It's a callable object, and functions are generally examples of callable objects. The parameter is going to be a dictionary, and the result is going to be a sample instance. At the bottom, I've shown a function named builder that fulfills that type hint contract. It accepts a dictionary and it produces a sample. Taking a second step down this path, the core of file reading can also be viewed as a callable object that emits the dictionaries that are converted by a builder. Taking a second step down this path, the core process of file reading can be viewed as a single external callable object, and that tends to open the design to extension. In this case, a row generator is a callable, for example, a function or callable object that will take any kind of parameter and will produce an iterator of dictionaries. And this matches CSV dict reader precisely, so the implementation tends to be pretty simple. The open-closed principle suggests these two features can then become parameters in other objects. In this case, we're providing values when we create an instance of the reader class. The row builder fits the pattern of a CSV dict reader. This is a pretty flexible interface, and we can build generators for new line delimited JSON and other file formats. Similarly, the sample builder converts output from a row builder into sample instances. I can provide alternative definitions to handle a wide variety of processing issues. The open-closed principle promotes the idea of adding features to a class through creating subclasses. There should be no need to tweak the code of a working class. Any tweaking indicates a failure to design a class that's properly closed to modification. In Python, the cost of a code tweak is very low. This can sometimes lead to poor designs with hard-coded constants and references to other classes. If a solid design avoids modification, how do we handle bug fixes? The idea of a class that's closed to modification sometimes leads to arguments among team members over how to implement bug fixes. I'm going to suggest that a class should be closed even to bug fixes. Really, what is a bug fix? It's a modification to a faulty class definition. If a class is truly closed to modification, what about the possibility of disruptive ripples that unfold from the change? Ideally, a bug fix has no ripples. Start with a bug report, create a unit test, revise the code, and hey presto, it's fixed, right? Well, not so quickly. Pragmatically, a design change may be made here to fix a bug over there. This is common because buggy behavior often emerges from the interactions of multiple objects. Bugs may not be confined to the internals of a single class. When making a change here to fix a bug that arises over there, the whole point is to leverage the ripple effect and fix the problem. And of course, this might introduce more problems. To minimize the destructive effects of ripples from any change, considering this approach to supplying bug fixes. Where possible, extend a class to introduce the bug-free subclass. Not all bugs can be fixed this way, and when a bug can be fixed by extension, this approach assures there are minimal ripples. Creating a new subclass means it's possible to leave the old buggy class in place. If the Liskov substitution principle is followed, the substitution of good for bad will work out nicely. Extending a class to fix the bugs will minimize the ripples. The class remained closed to modification. Leaving the buggy class definition in place leverages the idea of late binding. The runtime bindings provided by configuration files or command line parameters will avoid the buggy code. What possible reason can there be to leave it there? Consider the history of bad code. Bad code did go through some quality assurance. It appeared good enough to be released. When a bug surfaced, it's often because of a newly discovered edge case, perhaps an unforeseen user story. The process of discovery revealed new uses for the app, and that revealed unforeseen problems. This new user story means refactoring the design more than it means simply fixing the bug. The new design means reconsideration of all the solid design principles. It's handy to mark the buggy class as deprecated. The idea is to remove it later when major design changes are being made. The warnings module is often used for this kind of thing. In some languages, a class is closed to modification because it's frozen as compiled object code. In Python, the idea of closed to modification is severely limited. It requires careful documentation and unit testing, and perhaps explicit warnings to assure full cooperation. And yes, we do make some modifications. Our objective is to be reasonably consistent, avoiding the hobgoblin of foolish consistency. Here's the suggestion for bug fixes based on the open-closed principle. Modify code reluctantly. Extend code with subclasses eagerly. Let's say there's some suspicion that the correlation class has an algorithm that's too slow. Rather than modify the class, it makes more sense to extend the class hierarchy with another peer class that uses a different algorithm for correlation or linear regression or both. And this follows the Liskov substitution principle as well as the open-closed principle. What techniques are available to us? Python offers a number of ways of extending a class. In this section, I'll talk about two of the common techniques. Inheritance is the primary mechanism for creating a subclass to add or replace features of a superclass. Composition combines objects. There are a number of design patterns for this. For example, if a class uses the strategy pattern, then changes can be made via extension to the available strategy plugin functions or classes. We'll look at other ways to extend a class in the next section. And yes, the wrap versus subclass decision will be a recurring theme. When it comes to extension via inheritance, we don't have too many choices. Inheritance is sometimes treated as the only way to add features. The wrap or composition avenue, however, offers a number of implementation choices. As a practical matter, it's often necessary to combine the two. Let's look at an example of using composition to set the stage for extension. In some of the previous examples, I defined a correlation class that worked with a list of samples. The type hint list bracket sample bracket meant that it was the built-in list type, but the instances were expected to be sample classes. If we change this to use a counter object instead of a list object, the whole class would break. I find it helpful to refactor some parts of this computation into a separate sample list collection. I can then easily extend the sample list collection without breaking this correlation computation. Here's my sample list class that includes some of the computation steps I can later optimize if I need better performance. This sample list class extends the built-in list class, and it provides the additional methods for statistical computations. By building in sum, count, and sum of squares, it lets me replace a simple list object with this, or perhaps a class based on the more efficient counter object without breaking any of the client classes, like the correlation computation. Here's the correlation class that's simpler and easier to extend. It now has linear regression computations in it using the statistical methods from the sample list class. Here's another example. I've exposed the dependency between the reader class and an instance of the sample list class that it creates. I've made the sample list dependency into an attribute of the reader class. Extending this example, I've now exposed the dependency between a reader instance and an instance of the sample list class that it creates internally. I've made the sample list dependency into an attribute of the reader class. Now, a subclass of reader can use a different implementation of sample list with minimal ripples. This lets me upgrade to the new correlation and regression computation and the associated changes to the reader. Here's the final refactoring to create the regression computation. I've extended the base correlation class to include a new method that computes linear regression parameters. And I can do this because the two equations are so similar. Linear regression computes the two parameters that relate the engine RPMs and the number displayed on the radial tachometer. Here's the rest of the class definition. I've defined two methods, A and B, that will return the A and B attributes of the linear equation. Both of these rely on the compute method, and that method computes both values once and caches the results. Here's another example. Let's say I created a better, faster, smaller, more secure, or more auditable sample list class. In this example, I included a fantasy comment where I invented a cool new list algorithm that would be even faster. I can then incorporate this faster class into a reader by creating an extension to the reader class that will leverage the new faster sample list class. Similar refactoring can be done to the correlation and regression classes. The design pattern books provide endless examples of extensions that involve this kind of composition. The goal is to combine multiple objects to do a job. The resulting object has what they call emergent behavior. The behaviors aren't simply the methods of a single class. The reader class is an example of extension by composition. The sample collection class attribute names another class used to save and organize the sample instances. The open-closed principle looks at each class as being closed to modifications but open to future extensions. The idea is to avoid tweaking the source code to add or change a feature. The focus for all work should be some kind of extension to the previously released classes. In Python, there are a number of ways to add features to a class. We looked at only two in this section. The open-closed principle relies on keeping a class open for extension, but closed to modification. Python offers us a variety of ways to extend a class. In the previous section, I talked about the two most common techniques for extending a class, inheritance and composition. In this section, I'll look at three other ways to extend a class. Decoration rewrites a class. This works well when introducing a cross-cutting concern like security or application-wide logging. Mix-ins and multiple inheritance are ways to do class composition. And finally, functional composition follows from the ideas underlying functional programming. This design relies on nested function calls instead of sequences of object methods. A Python decorator is a function which transforms an original class definition into a modified class definition. It's a way of rewriting a class to extend it. It works best with things like audit and security that apply to a wide variety of application classes. The interface segregation principle suggests that these features need to be segregated from other features. Here's a definition of a simple decorator, logged. A decorator is a function that rewrites a class. In this example, the decorator assures that the class will have the logger attribute. The decorator can be applied to application classes to assure consistency. This is a runtime modification to a class. It's a modification that MyPy can't follow and will lead to error messages. Here's how this decorator can be applied to the reader class. Now, we can use self.logger.error to write error messages for log rows that can't be properly read. The logger decorator assures that the logger attribute is present in every class that has the decoration. As I noted above, the MyPy tool doesn't follow these kinds of runtime modifications to a class. That's why there's a special comment to silence the mismatch between the obvious class declaration and the actual runtime attributes that will be present in objects of classes that are decorated. Python allows a class to have any number of superclasses. The mix-in design pattern distinguishes between the essential features of an object and extra features mixed in with those essential features. The term multiple inheritance is a more general term for combining class definitions. I find the mix-in design pattern really helps to separate the essential definitions from features that get combined into that essence. This class definition defines methods that can be applied to any kind of collection of sample instances. When we look at the collections.abc package in the Python standard library, we see that a sequence is a kind of a collection, and the list that we often use is a kind of sequence. The idea of depending on the collections abstraction is the interface segregation principle in action. We're depending on the smallest interface possible when we define these statistical functions. The mix-in concept combines classes to create a new class. This lets the groups of features evolve independently. A one-line class definition can combine the subclasses of list, called list bracket sample bracket, and the stats method class, and it creates something new. The resulting sample list class has methods defined by two different base classes. Classes are searched in the left to right order, so if we provide duplicate methods, that tells us what order they will be resolved in. The diagram shows a lattice of relationships among the classes. The design segregates two features, the essential list of samples structure and the statistical processing methods that apply to any collection of objects. Given two separate partial class definitions, I can combine them. This applies a reusable set of statistical methods to a list of samples. Each is independently open to extension. New combinations can be defined from extensions to one or both of the parent mix-ins. This kind of design more narrowly constrains the ripple effects by isolating the two interfaces into separate classes. The final extension technique that I want to look at comes from the realm of functional programming. Instead of building stateful class definitions, it's possible to tackle many problems using stateless function definitions. The goal is to have functions that can be combined in different ways. Here's an example of using several higher-order functions to create a composite function definition named sum. I like to look at this kind of definition from the inside out. First, the adder-getter function is applied to the attribute name, and it creates a function that returns the named attribute value from each sample instance. Then, the map function applies the attribute extracting function to each item in the self collection. And finally, the built-in sum function adds up the values created by the map function from the results of the adder-getter function. Each of these pieces is small and reusable. The overall composite object is built from pieces that can be closed to modification. The open-closed principle looks at each class as being closed to modifications but open to future extensions. The idea is to avoid tweaking the source code to add or change any features. The focus for all modifications should be some kind of extension to the previously released classes. Python offers a variety of techniques for extending a class. Each has its strengths and limitations. If I need to modify a class, this can introduce a destructive ripple that might have unintended consequences. If, on the other hand, I extend a class, then no previously existing code needs to be damaged.